Okay, good morning, everyone. Yeah, it's 9 a.m. and we can start. So, in the previous lecture, we finished discussing Faraday's law, and after that, we moved and started introducing inductors or induction in general, right? And why inductors follow Faraday's law? Follow Faraday's law because to explain the work of an inductors, we need to know Faraday's law, right? So it logically follows, right? Okay, so now let me remind you a few major points about inductors, induction in general, right? And then we will start solving problems. First, what's the role of an inductor in a circuit, right? Because inductor is a typical element of any circuit. It allows us to store energy, but in the form of the magnetic field, right? You remember in a similar way I introduced the role of a capacitor, right, a couple of months ago, right? So back then capacitor allowed us to store energy in the form of the electric field. Now inductors allows us to store energy, but now in the form of the magnetic field. So it stores energy and then you can use it, I know, microsecond or millisecond later, right? Then let's introduce an induction. And since a solenoid is a typical inductor, so most of the time I'm going to draw a picture like that, right? So let's assume that we have an inductor. And current, you send the current through that inductor, in this case solenoid, right? Of course, this current, of course, is going to create a magnetic field inside of this solenoid. It will be something like this, right? So B, magnetic field. And so now we have magnetic field, we have tons of loops, right? Because what is solenoid effectively? It's a bunch of loops stuck together, right? And so there is a magnetic flux through one loop, and then of course you can calculate the total flux, right, by adding fluxes produced through each of those loops, right? So you can calculate total flux. Now, if you start playing with these two parameters, total flux and the current which produces all this mass, you will be surprised, or maybe not surprised, right? If you take the ratio of the flux versus current which produces all this mass, that will be exactly the same number all the time, of course, within experimental error, right? So if that is constant, it makes sense to think that it's that constant is some kind of an intrinsic property of this object. So let's give it a cool name: inductance. Induction sounds cool enough, right? So as a result, we can introduce induction as L, right? L equals. So by definition, 3 lines. By definition, it's a total flux divided by the current. So that's how induction is introduced. Okay, let me frame it because it's a definition. And so now, since you introduce a new quantity, logical question: should we introduce a special unit? And the answer, of course, yes, because inductors are used everywhere, right? Very, very common circuit element. So it makes sense to give a special name for the unit, right? So units of inductance is Henry. Right. And of course, what is 1 Henry? It's a Weber divided by amps. Weber divided by amps. Weber units of the magnetic flux. Okay, so then, how it is usually shown in the circuit? Of course, since the solenoid is a typical inductor, so usually something like this, right? Then, what else? Okay, so now, this is definition of inductance in general. And it can be applied to find inductance of any object, right? You can find inductance over, I don't know, a piece of wire, right? You can find inductance of, I don't know, of this loop. You can find inductance over a solenoid. You can find inductance of me. Again, it's a general definition of inductance, and then you just apply to calculate a particular formula, over a particular object, inductance of a particular object, right? So since we're going to use solenoid all the time. So we calculated in the lecture the inductance of a solenoid. Again, we just applied this formula to calculate inductance of a solenoid. Okay, so now let me write that down. So this will be my first small bullet. Now the second small bullet, solenoid inductance. Solenoid inductance. Okay, so I will write it here. Yeah, solenoid inductance L equals mu naught n squared and number of loops in a solenoid, right? Then times area. Right, so over here, this is cross-sectional area, and divided by the length of the solenoid, L, right? Okay, of course, we should frame it because we use it quite often. Then, what's the major feature of this formula? Mu naught describes material. In this case, inside of the solenoid, there's a vacuum. Okay, so mu naught tells us that inside of the solenoid there's a vacuum. Then n, number of loops, geometry. A, cross-sectional area of the solenoid, geometry. L, length of the solenoid, geometry. It's all about the geometry. It doesn't depend on the magnetic field or a magnetic flux or current or any other electromagnetic quantities. None of them are here. Only material and geometry, right? Sort of similar we saw when we introduced, you remember, the capacitance of a parallel plate capacitor. Very, very similar words I pronounced, right? So now, in general, lots of similarities between capacitance and inductance, right? But capacitance plays all these roles in the world of electricity. Inductance plays all these roles in the world of magnetism, right? Then, after that, we looked at the potential difference across the solenoid. Potential difference. Right. Across it, okay, maybe let me write. Across a solenoid. Okay, we're going to use most of the time solenoid. Right. Okay, so we derived the formula, right? Using Faraday's law, because again, as I told you, Faraday's law is behind all this mess, right? Right. EMF equals to minus d phi over dt. Right. Of course, you can ask me how come that you use the formula for a loop to find the potential difference between what? This is the final point of the solenoid exit, and this is initial point of the solenoid entrance, right? So we're trying to find delta V across the solenoid. The thing is, okay, solenoid effectively is just a bunch of loops stuck in the same structure. Of course, we can find EMF across the first loop. It will be EMF1 using this formula. Then next loop, EMF2. Then next loop plus EMF3, and so on over a few hundred loops. If you add them all up, you will get the total potential difference eventually between this final point and initial point, right? So pretty much we can use the same formula, right? And now this EMF, it's a total EMF across the solenoid, and we can call it delta V, all right? And in order to get what we derived in the class, we just use this definition of inductance, right? So, okay, it's a magnetic flux. So magnetic flux equals L times I. So you plug it and you will end up with minus. L is the constant. Where all the time, if you pick a solenoid, we usually don't change the shape, or we don't change the its geometry. So L stays the same, right? And di over dt. So the formula which we wanted, delta V equals minus L and di over dt. Okay, we need to frame it because it's important And again, emphasizing what is a delta V. This is, okay, which color should I use? Probably this. All right. This, the point where current exits the solenoid, it's the final point. This, where current enters the solenoid, that's initial point. So delta V, it's a V final minus V initial. Right? So that's what delta V is, right? Okay, and now let's look at three situations: when current constant, when current growing, and current dying, right? All right, so let's quickly look at that. So first, let's look at the situation when original current through the solenoid is growing. It means that di over dt is, di over dt is positive. Di over dt is positive, right? So as a result, di over dt is positive, minus in front. So we're getting the delta V is negative, right? So let me draw. Delta V is negative. So what does it mean, negative? It means that V final is smaller than V initial. Because delta V, it's a V final minus initial. So it means that the potential at the final point is smaller than the potential at the initial point. Let me redraw this picture very quickly. All right, so let's say this is our solenoid. And this is, okay, let me make it bigger slightly. And let's assume that this is a battery which drives this original current. Maybe I can put sub-zero, I don't know, sub-zero. Right. So this original current, right, so this is I naught. And this current driven by this battery is growing. So now this delta V equals, delta V is negative, it's a response of the solenoid. So since solenoid has some amount of energy, it can use that energy in some way. So in this case, it used that energy to produce an additional potential difference, which is not produced by this battery. No, it is produced by the solenoid. And again, you remember this, the point where current leaves the solenoid. So this is the final point. Again, let me emphasize. So this is a final point. This is initial point, right? So V final potential at this point is smaller than potential at the initial point. So this is minus. Here we have plus. Okay, so effectively, solenoid starts working as a small battery with this polarity. So here we have plus, here we have minus. And this effective battery starts driving its own induced current. In which direction? From this plus to that minus through the rest of the circuit. Oops. So I induced in the opposite direction to the direction of the original current. So now we can develop a mnemonic rule. Effectively, it's a Lenz's rule behind all this. But if you start applying Lenz's rule, it's not very practical. It's not very practical. Some additional steps you have to make. It's better to readjust Lenz's rule slightly and state it in a different way. And the rule is like this. So this solenoid doesn't like when current changes through the solenoid, right? So look, if current is constant, the solenoid doesn't respond. Delta V will be 0. If current is constant, this is 0, then delta V is 0. So in that case, solenoid doesn't do anything. The solenoid is happy, sleeping happily, right? But once you start changing current, in this case, current through the solenoid is growing, the solenoid wakes up immediately. You're changing current through me. Okay, I don't like that. because the solenoid wants to keep current constant. It's like in the Lenz rule, the loop tried to keep flux constant, but now it tries to keep current constant, original current as constant as possible. So here now current is growing, solenoid doesn't like it, and it responds with producing higher potential at the entrance of the solenoid and lower potential at the exit of the solenoid, and as a result it drives an induced current, secondary current, in the opposite direction to suppress the growth of the original current. It's basically again Lenz rule, but now it's better to state about the fact that the solenoid doesn't like when current changes, right? Okay, so now let me state it. Which way I wrote it. Okay, so the rule, right? If original current is growing, right, then I induced current will be in the opposite direction to the I original. Okay, and right underneath, it rebels. Right, so it tries to suppress the growth of the original flux. Original current. It's sort of like rebels now. It's the same story, but now it's about current, original current. Right. Okay, so now the second situation. What if original current is dying? What if original current is going down? So then, of course, rate of change of the current, di over dt, is negative. And of course, so now negative di over dt minus also in front, so delta v will be positive. So delta v is positive, right? And again, what is delta v? It's v final minus v initial is positive. And it means that v final is larger than v initial, right? So it means that potential at the final point is larger than potential at the initial point, right? Okay, so now let me draw the picture and analyze direction of the induced current. Okay, let me draw the same picture. So this is the battery, which drives an original current. Again, original current goes from plus to minus of this battery, so it's I naught. But now this current is dying. I know you have here a potentiometer. Let's say you crank it down, right? Okay, so now response of the solenoid. The solenoid doesn't like that the current is going down. So in this case, it responds. Again, this is the final point. This is initial point, right? So potential at the final point is higher than potential at the initial point. So now the solenoid starts working as an effective battery with the opposite polarity. So here plus, here minus, right? Opposite to this. So now plus on that side, minus on this side. And it means that this solenoid, since it creates its own potential difference, it starts driving induced current in this direction from this plus to that minus. So now induced current is in the same direction as the original current, supporting the dying flux or dying current. Again, the same words like we pronounced with Lenz rule, and that's why every time flux jumps out of me, right, instead of current. All right, so now I can state the rule, right? So if original current is dying, going down, then the solenoid responds with the proper potential difference, right? Delta V is positive, so that as a result, I induced is in the same direction as I original, right? So in this case, it supports the dying current. So the system becomes supportive, like Florence Nightingale. You remember all those words, right? Okay, And of course, if current the last.
Can you read the blue
Yeah?
text again? Can you read what you wrote in blue again?
This?
Just above that.
I induced, current induced, IND, and the same direction. You see two arrows up as I original.
Okay, got it.
Yeah. Okay. Sorry, I should have been. It just when I move lower and lower in the terms of the whiteboard, it's more and more difficult to write because here I have
No worries.
horizontal surface, right? Okay. So, and of course, the situation if current is constant, then the solenoid is completely happy and it doesn't do anything. Constant, then as a result, delta V is 0. And in this case, inductor or solenoid is just a piece of long wire which doesn't do anything in the circuit. Okay, so now that's what we needed. And now let's look at a few problems. Questions about this. All right, we will look at a couple of conceptual questions I like to give on the final exam. And the results are I don't know, 40 to 60. Oh, 60 to 40% probably. Okay, so this is also old stuff. So 25. Still chapter 30, problem 25. So what do we have here? We have an inductor, basically solenoid, right? So induction is given 100 milli units Henry, right? Milli H, right? Then something happens to the current flowing through that inductor, because if nothing happens to the current, then nothing we could discuss. Right. So what? Initial current I sub I, 150 milliamps. Then after some time, this current goes down and the final current is 50 milliamps. And it all happens in the period of time of 10 microseconds. Right. So we need to answer the question, what happens to the potential difference across the solenoid? It's basically this picture, right? Maybe, you know what, I will draw it immediately. Right, so that's battery which drives this current. Again, I will use probably the same color, right? So this is the current, this original current, which changes. And we need to answer the question, what happens with the potential difference across this solenoid? Okay, let me show something like this. So this is delta V, which we need to find. And again, you remember, the point where current exits the solenoid, that's the final point, and the point where current enters, that's the initial point. Okay, first let's answer this question conceptually. Probably let me state, so we need to find, wrong color, okay, sorry, delta V. That's what we need to find. And first, let's discuss conceptually. Okay, what we know? What happens to the current? We know what happens to the current. Current is going down, right? Current is going down, so it means that according to that modified Lenz's rule, we know what we know the response of the solenoid. Current, original current is going down. It means that it's a this situation. Original current is going down. As a result, the induced current will be in the same direction as the original current, right? System becomes supportive, right? So let me show that. So since original current is going down, so we can write immediately that induced current will be in the same direction as I original. So it means that, being supportive, right? It means that in the same direction means it's this way. So this will be direction of I induced, right? And so now, what should be a polarity of this effective battery in order to drive the current, induced current, like that? Here we should have higher potential, here we should have lower potential. So here we should have plus and minus. So it means that at the exit of the solenoid, we should have higher potential, and here we should have lower potential, right? So as a result, delta V, which is final minus V minus initial, is positive. So as a result, delta V is positive. So that's what we should get. Now we're going to calculate it. But first I want to discuss it conceptually using this sort of modified length rule. Again, the steps. We know what happens to the original current. Current is dying. Solenoid, according to this modified length rule, doesn't like when current changes. It responds immediately. And we know the response. If current is dying, the system, the solenoid, becomes supportive, like Florence Nightingale helping dying creatures, right? So it starts driving an induced current in the same direction as the original current. So now we see direction of the original current. We know now the direction of the induced current, the same. And now we know that this induced current is produced by the potential difference, which we want to find. So in order to produce this current, here we should have, here at the end, we should have higher potential, and at the entrance we should have low potential. So that's what conceptual. And usually about this discussion, sort of a conceptual discussion, I usually organize the questions on the final exam. A question on the final exam among multiple choice questions. Okay, so now let's calculate. Let's calculate delta V. Right. Okay, so what? The formula is here, so let's just apply it. Right. Delta V equals minus L and di over dt. Di over dt. Okay, so now I start criticize the author of the book, right? Because I claim that problem is not stated properly. Because one important piece of information is missing in order to continue from after this point. Because look, we know only the value of the current at the final point and the initial point, and not a single word what happens to this current, how it changes, right? Maybe it changes exponentially, or maybe a logarithm, or maybe somehow else, right? Not given. Of course, we know that most likely the author assumed that we would assume that current changes linearly, right? But you should state that. Right? So it's a right. So I'm going to write, let's assume current changes linearly. Otherwise, we wouldn't be able to solve the problem. Right? Otherwise, it will be more complicated. So I will open my explanation box and write, assume I changes linearly. Oops, my cylinder fell down. So if current changes linearly, what can we do with this di over dt? We can rewrite it as delta I over delta t, because what is di over dt? It's a slope of the curve, how current changes with time. But if the curve is straight line, then it doesn't matter. If you calculate the slope using an infinitesimally short period of time, delta t, or dt, or a finite period of time, delta t, because it's a straight line, slope is the same at every point, right? So as a result, we can write as minus L and delta I over delta t, right? Okay, so now let's write explicitly. Delta V equals to minus L, and it will be I final minus I initial divided by delta T. Final and initial are given. So now we just plug numbers. Minus 100 times 10 to the power of minus 3 Henry, right? 100 millihenry units, I mean, the value of inductance, and then in final 50 minus 150, and milliamps I will take outside of the bracket. So the milliamps I factored out. And divided by delta T, which is 10 times 10 to the power of minus 6 seconds. And be careful with initial and the final current. Right? You need to use them properly, right? So here we're subtracting larger number from the smaller, so we're getting negative value and minus in front. As a result, change in the electric potential is positive, right? So let me look at the number, at the answer. So it's 100 volts plus 100 volts. So yeah, we got conceptually positive number, positive value, and now we calculated that the potential difference across the solenoid is positive. Again, you need to realize that this is response of the solenoid. This potential difference is produced by this solenoid, not by this battery. The solenoid produces because it's unhappy, right? It feels that current changes and it responds somehow, creating the potential difference across itself, right? Because it's unhappy. Right. Okay, so that's how I would analyze, right? Usually calculations is quite simple, but conceptual analysis, that's where students have issues, right? On the final exam, where if I assign problem like that. Okay, we will practice more. And now let's look. Okay, guys, if you have some particular questions, ask at any moment, right? Okay, so I'm just checking if I mentioned everything. Yeah, it looks like. Okay, so the next one, problem 66. You know what? I don't want to erase this because I need that for discussions. 66. Okay, so now again we have an inductor in some simple circuit, and inductance the same. So we have an inductor. Inductor, and inductance is 100 again millihenry. And again, there must be something happening to the current through this inductor. Otherwise, there wouldn't be anything to discuss, right? If current is constant, solenoid inductor is happy, and delta V will be 0, right? It will be just a long piece of useless wire in your circuit, right? So current changes according to the plot. Plot is given, how current changes. Okay, so now let me plot that. All right, so I have to draw it carefully. So let's say this is current, units of amp, right? Then time in milliseconds. And what, 1, 2, okay, up to 6. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. And now, so first current growth up to point of 2 milliseconds linearly. Then it stays constant for 1 millisecond up to 3 millisecond point, and then it goes down to -2 at 5 millisecond point. And then it stays constant again up to 6 millisecond point. Okay, so that's how current changes with time. Okay, let me make this line thicker. And this is 2 amps, and this point is -2 amps. Okay, so what we need to do, we need to plot. Okay, so first of all, you see now we know what happens to the current through the solenoid, through the inductor. And of course, now we need to apply all these 3 rules in order to figure out what happens to the potential difference across the solenoid. Is it positive? Is it negative? What's the value of the potential difference? Because again, as I said, solenoid, if current changes, solenoid is not happy, and it starts producing its own potential difference across itself. Very self-sufficient solenoid, right? Okay, so now what we need to plot? We need to plot how potential difference changes with time. Again, millisecond. Right. And so the same points, 1, 2, okay. Let me put them closer. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we need to plot that. Okay, now I need to erase this top. So it's all about this formula. Of course, we can analyze conceptually, but eventually, in order to calculate, of course, you'll have to apply the delta V equals minus L and di over dt. And now I'm going to write the same what I wrote here, because now we see current changes linearly all the time. Okay, not all the time, but in these pieces, in the section number 1, section number 2, you see, in these sections, current changes linearly. So if we apply that formula for each of these sections, so we can slightly adjust that formula with this minus L delta I over delta T. Instead of di over dt, we can use finite increments, right? But of course, we need to divide into several sections, 1, 2, 3, and then section number 4, right? And for each of these sections, we can apply that formula 4 times. Okay, so now let's do section number 1. All right. Okay, so delta V over here, it will be, of course, minus. You know what? I will start writing immediately numbers. All right, 100 millihenry. So it's a 0.1 Henry. 0.1 Henry. And then the delta I, it's a I final minus I initial. Final value in the first region, 2 amps. That's the final point. Initial point is 0 amps. So it will be 2 amps minus 0 amp, and divided by this stretch of time over which it happens, 2 milliseconds. This stretch of time, 2 milliseconds. So it's a 2 times 10 to the power of minus 3 seconds, right? So the response, the potential difference across the solenoid will be negative, right? Current is growing. Basically, conceptually, current is growing. It's at this situation. the solenoid is not happy. It starts producing the potential difference so that induced current will be in the opposite direction. So the current flow in the opposite direction. So the electric potential at the entrance must be higher than the electric potential at the exit. So as a result, the delta V is negative, right? So it's a V final minus V initial. We have delta V is negative. So that's the situation we have, right? But now we're just calculating and we will getting pluses and minuses automatically from the formula. So let me look at the answer. Minus 10 volts. Minus 10 volts. Okay, so now I can plot the first part of the graph. Okay, I will use probably blue. So let's say this is minus 10 point, right? And first it just stays constant delta V over that stretch of time. The first section over this section, potential difference is constant and it's negative across the solenoid. So this situation, induced current is in the opposite direction to the original current. Okay, so now next, the second section. What can you say immediately about the second section? Current stays constant. The solenoid is happy completely, right? So it doesn't have to do anything because current doesn't change. Current stays constant. So the solenoid doesn't do anything. So immediately I can draw, okay, maybe I will write first, second section, right? So of course, delta V is 0 since current is constant. Okay, so now I can draw this. It's over 1 millisecond. Okay. Now the third section. So now current changes again. The solenoid again wakes up to do something, right? So delta V. Actually, we can first get conceptually what will be the response. So you see what happens to the current. It's going down in time. Current is dying. It's this situation. So of course the system becomes supportive to support dying current. All right. So it means that in order to drive current supportive, it means it drives induced current in the same direction as the original current. So it means that it drives that way. So it means that at the exit of the solenoid, final point, potential must be higher than the electric potential at the initial point. So as a result, delta V, again, V final minus V initial must be positive. So that's conceptually, but now let's calculate from the formula. So it will be minus L. We agreed I will write immediately numbers because the formula is over there, 0.1 Henry. And so now, final point, carefully, this is the final point, minus 2 amps. Then minus initial point, 2 amps. Again, minus from the formula because we're looking what at delta I. Delta I, it's a final value of something minus initial value of something. Minus 2 amps and divided by, again, so hold it. What's the, stretch of time also. 5 minus 3, let me write explicitly, so it will be 5 minus 3 times 10 to the power of minus 3 seconds, milliseconds, right? So 2 milliseconds. So minus from this ratio, minus in front, so the potential difference will be positive like we just discussed conceptually. Right. So what's the answer? 20 volts plus 20 volts. Okay, so now we can draw that part of the graph. So between 3 and 5. So now, so let's say this is 10, this is 20, right? So between this and this, current stays constant and positive, 20 volts. And the last section from 5 to 6 milliseconds, immediately you can tell the solenoid is happy and is not going to do anything, right? So current is constant current, the slope is 0, delta V is 0. So the last section, number 4, it's like in the second section, delta V will be equal 0 since current is constant, right? Okay, so now I can draw it here. Okay, so that's the plot. Okay, we applied this trick, but for different physical situations so many times that I doubt that you have any problems with understanding of what we've done here. Okay, so now conceptual questions. Since we still have 4 minutes left. Conceptual question 11C. Okay, I need to erase this lower part. Right, so now let me separate this. So CQ 11C. CQ, conceptual question, at the end of the chapter. Chapter 30. Right, okay, maybe I will draw the situation here and then I will erase. Right, let me keep it longer a little bit. So what is given? A solenoid is given. Inductance is given. So L equals to 2 Henry inductance. Then there is an original current. Okay, let me use again red. Right. And this time it's called I1. Okay, why not? I1. So that's the original current. Okay, let me emphasize that this is original current. Okay, now I need to erase the rest. Then something happens to this original current. What do I mean by something happens? It can grow, it can go down, it can stay constant. 3 situations. But something happens, and as a result, solenoid response. We see the response of the solenoid in terms of the potentials, electric potentials, right? So response of the solenoid, it creates higher potential at the exit. So basically, this is the final point because you see original current flows that way. So this is our basically final point, and this is our initial point, right? So we see the response of the solenoid, and the value of that response is also given. Delta V equals 2 volts. Delta V equals 2 volts. And so that's what is given. We need to answer the question, what? Yeah, we need to answer the question, what happens to the original current? Okay, so let me write, so what happens to I1? In terms of, first, conceptually, is it growing, is it dying, right, and so on. Oh, okay, let me finish this question, right? Okay, so that's what is given. And in order to make it picture even look better, at least in my opinion, let me add this battery which drives the original current, right? Okay, so let me, okay, I will use probably different color, right? So this is, and so what should have, which polarity we should have, since original current going that way. So here we should have higher potential, and here we should have low potential. So battery like that. Right. Okay, so now in order to find out what happens to the original current, we need to figure out what about the directions. What can we say about directions of the induced current and the original current? Induced current and the original current. If they're in the same direction, like here, we can say immediately that the original current is dying. If they're in the opposite directions, then we can say immediately system rebels. It means that the original current is growing. So let's see. We see the response of the solenoid. Delta V is positive, right? So effectively, it works. Again, I can draw over here like a small battery like this, right? Plus and minus. And of course, since higher potential over here, this solenoid drives current this way in the same direction as the original current, right? So I can draw something like this. So that's I induced, right? Okay, I can even explain why very often I draw this effective battery, right? Because you see, I've seen in the past, right? So here plus, here minus, right? And now in order to find out direction of the induced current, many students made this mistake. They know the current should flow from plus to minus, and they see this big gap between this plus and this minus, and as a result, they draw induced current downward in the wrong direction. No, this plus and minus is produced over here. This is the like a workstation, right? Producing this plus and minus, and then this current should flow through the rest of the circuit. That's why every time I drew this small battery, so that I squeeze this gap between this plus and minus, so that students wouldn't make the mistake and pick the wrong direction of the induced current. Induced current must flow through the rest of the circuit, through the loop, right? Okay, so this plus and minus, of course, they produced induced current flowing counterclockwise, which is the same direction as the induced current. So the same directions. It's this situation, so the original current is dying. So usually these type of questions I give on the final exam among multiple choice questions. And the outcomes usually, as I said, I know 60 to 40, 60% of correct answers, 40% probably sort of like with mistakes or completely wrong. Right? So conceptually, but actually it's just a few steps. If you know this sort of modified length rule, modified for the case of inductors. Right? So in this case, let me write something like this. So since I induced is in the same direction as the original current we just established, right? So as a result, we can say that original current I1 is dying. Yeah. Hold it. Ah, yeah, dying. Yeah. In the same direction. So original current is dying. Okay. Thank you, guys. If you have questions, go ahead. If not, then I will see you tomorrow on the lecture.